It begins, as it always has, with a glance upward, into the deep, velvet canvas of the night, a tapestry pricked with diamond-sharp points of light. For millennia, this was our universe. A familiar, comforting dome of constellations, a celestial clockwork that governed our seasons, our myths, our very sense of place in existence. We saw the shimmering river of the Milky Way, our own home, and believed it to be the grand total of all creation. A solitary, magnificent island of light, adrift in an infinite, empty ocean. We were profoundly, beautifully, and reassuringly wrong. The truth is not written in the few thousand stars our naked eyes can perceive. The real story is whispered from the darkest, most unassuming patches of the void. It's a tale of such staggering scale, such mind-altering complexity, that it redefines not just our world, but the very nature of what it means to be. This is the story of a cosmos far grander than we ever dared to imagine, a universe not of one island, but of trillions. The journey to this revelation was not a sudden leap, but a slow, painstaking climb out of the darkness of assumption. For most of human history, our cosmos was intimate, its borders defined by the power of our own vision. Ancient Greek philosophers, with brilliant geometry and logic, mapped the heavens as a series of celestial spheres, crystalline shells with Earth at their divine center. Everything, the sun, the moon, the wandering planets, and the fixed stars, revolved around us. This architecture of the heavens was elegant, it was intuitive, and it dominated Western thought for over 1,500 years. But the universe has a habit of challenging our most cherished certainties. A Polish astronomer, Nicolaus Copernicus, dared to suggest a different arrangement, a heliocentric model that placed the sun at the heart of things. His idea was revolutionary, so much so that he delayed its publication until he was on his deathbed. Then came the telescope, a simple instrument of curved glass that would forever shatter the crystalline spheres. In the hands of Galileo Galilei, this spyglass became a window onto a new reality. He saw mountains on the moon, revealing it to be a world, not a perfect celestial orb. He discovered 4 new moons orbiting Jupiter, a miniature solar system that proved not everything revolved around the Earth. Our planet was demoted, our central place in creation revoked. Yet, even with this monumental shift in perspective, the scope of our cosmos remained contained. The stars, now understood to be distant suns, were all believed to be part of one colossal city of light, our Milky Way galaxy. Astronomers like William Herschel in the 18th century undertook the Herculean task of mapping this stellar metropolis. By meticulously counting stars in different directions, he constructed the first model of our galaxy, a flattened, grindstone-shaped system. It was a masterpiece of observational science for its time. But Herschel, like all before him, still believed he was charting the beginning and the end of everything. The faint, fuzzy patches of light he and others catalogued, the nebulae, were thought to be nascent solar systems, cosmic clouds of gas condensing within our own galactic borders. The idea that they could be something more, something impossibly distant and unimaginably large, was a frontier of thought few were willing to cross. That frontier became a battleground in the year 1920, at what would become known as the Great Debate. On one side stood Harlow Shapley, a brilliant astronomer who had accurately measured the vast size of the Milky Way. He argued that our galaxy was the entirety of the universe, and that the spiral nebulae were mere local phenomena. On the other side was Heber Curtis, who contended that these spiral structures were something far more profound. He proposed they were island universes, entire galaxies just like our own, scattered across an even vaster expanse. Science had reached a monumental impasse. Was our existence confined to a single galactic system, or was our home just one of countless others? The answer would not come from debate, but from observation. It would arrive from the cold, clear air of a California mountaintop through the eye of the world's most powerful telescope. And it would be delivered by a man whose name would become synonymous with the modern cosmos, Edwin Hubble. Hubble was a meticulous, almost stoic observer. Night after night at the Mount Wilson Observatory, he used the colossal 100-inch Hooker telescope to capture faint light from the Andromeda Nebula. His goal was to find a specific type of star, a Cepheid variable. These stars are extraordinary cosmic mile markers. They have a unique property discovered by astronomer Henrietta Leavitt. Their brightness pulsates at a rate directly related to their true intrinsic luminosity. They are standard candles. If you measure how fast one of these stars pulses, you know how bright it truly is. By comparing that absolute brightness to how dim it appears from Earth, you can calculate its distance with astonishing precision. It is like seeing a 100-watt light bulb in the distance. Because you know its true power, you can judge how far away it must be based on its faintness. In October of 1923, after years of patient work, Hubble found what he was looking for on a photographic plate of Andromeda's outer arms, a single, flickering point of light. He meticulously calculated its distance. The number that emerged from his equations was staggering: 1 million light-years. This was a distance so immense it placed Andromeda far, far outside the most generous estimates for the edge of the Milky Way. In that single moment of calculation, the known universe exploded. The fuzzy patch of light was not a cloud of gas within our home. It was an entire galaxy, a sister city of stars, larger than our own, across an abyss of space so profound it defied comprehension. The island universe theory was confirmed. The great debate was over. Humanity suddenly found itself adrift in a cosmos populated not by one galaxy, but by countless others, each a swarm of hundreds of billions of suns, each potentially with planets of its own. Hubble's discovery opened the floodgates. Where we had seen one galaxy, we now saw 2, then 100, then thousands. As telescopes grew more powerful, the census of the cosmos expanded, revealing a universe strewn with galaxies of every conceivable shape and size. Elegant spirals with majestic, sweeping arms, massive, amorphous elliptical galaxies, like giant, disordered swarms of ancient stars, chaotic, irregular galaxies, forged in the violence of cosmic collisions. For decades, our best estimates, our most educated guess, placed the total number of these stellar cities at around 100 to 200 billion, a number so large it already strains the limits of human imagination. But the universe was holding its greatest secret in reserve. The true count was far, far higher. To find it, we had to do something that seemed completely counterintuitive. We had to stare into nothingness. In 1995, astronomers made one of the boldest gambles in the history of science. They decided to point the Hubble Space Telescope, humanity's greatest eye on the cosmos, at a patch of sky near the Big Dipper that was utterly, profoundly empty. The spot was minuscule, the size of a grain of sand held at arm's length. It was chosen precisely because it contained nothing of interest. No bright stars, no known nebulae, just the blackest ink of the void. The plan was to expose the telescope's camera to this void for 10 consecutive days, over 100 hours of observation. The hope was that by collecting the faintest, most ancient photons of light, something might emerge from the darkness. Many in the astronomical community thought it was a colossal waste of the telescope's precious time. The risk was immense. The result could very well be a long, expensive, and completely blank image. As the data streamed back down to Earth, bit by bit, the image was slowly assembled. And what it revealed silenced all the critics. It changed cosmology forever. The image was not blank. It was not empty. It was overflowing. The tiny, dark patch of sky was ablaze with light. But these were not stars. Nearly every single speck, every fleck of colour in that frame was a galaxy. 3,000 of them, crammed into a sliver of the heavens that had appeared to be a vacuum. This was the Hubble Deep Field. It was a core sample drilled down through the depth of cosmic time. The light from the nearest galaxies in the image had travelled for hundreds of millions of years to reach us. The light from the faintest, reddest smudges had been journeying for over 12 billion years, originating from a time when the universe was just a toddler. We were not just looking out into space. We were looking back into the deepest history of creation. Imagine standing in a dark forest at night. You can see the trees closest to you, but if you stare into the gaps, into the deepest, darkest parts of the wood, your eyes slowly adjust. You begin to make out the faint outlines of trees much farther away, and then even more ghostly shapes far beyond them. The Hubble Deep Field was humanity's eyes adjusting to the true depth of the cosmic forest. We had been blind to the sheer density of existence. This groundbreaking image was repeated, creating the Hubble Ultra Deep Field and the E-Extreme Deep Field, each one pushing deeper into the primordial darkness. Each time, the result was the same, a canvas saturated with galaxies. But these images, as revolutionary as they were, still held a fundamental bias. Even the mighty Hubble telescope has its limits. It can only capture light that is bright enough to register on its sensors. What about the galaxies that are too small, too faint, or too distant to be seen directly? A new generation of astronomers took the data from the deep fields and combined it with our most advanced theories of galaxy formation and evolution. They constructed a sophisticated three-dimensional model of the observable universe. They could then calculate how many galaxies times exist in any given volume of space, even if they were too dim for us to detect. It was like mapping the population of a vast, continent-sized city at night. You can see the bright lights of the downtown cores and major boulevards, but you know that for every visible streetlight, there are countless unlit houses, tiny cottages, and dark alleyways that are still part of the city. The astronomers were calculating the population of those unlit cosmic neighborhoods. When the calculations were complete, the number they arrived at was a revelation that dwarfed even Hubble's discovery. Our previous estimate of 200 billion galaxies was off by a factor of 10. The true number, the most accurate census of our observable universe, is at least 2 trillion galaxies. Let that number sink in. If you were to count one galaxy every second, it would take you over 63,000 years to finish. For every single star in our own Milky Way, there are 10 entire galaxies out there in the void. The vast majority of them, over 90%, are completely invisible to our current technology. They are ghost galaxies, their faint light lost in the immeasurable gulfs of space and time. Our real universe is one we cannot even see. The glittering deep field images, which we thought revealed the extent of creation, are merely the brightest treetops of an infinite jungle. To truly comprehend our place, we must venture inside one of these stellar cities. A galaxy is not merely a collection of stars. It is a living, breathing, dynamic ecosystem of cosmic matter and energy, governed by forces on an unimaginable scale. At the heart of nearly every large galaxy, including our own Milky Way, lurks a monster. A supermassive black hole. These are not the black holes formed from collapsing stars. They are primordial beasts, millions or even billions of times the mass of our Sun, packed into a region smaller than our solar system. For decades, we could only infer their existence by the frantic dance of stars orbiting an unseen center. But recently, with a global network of radio telescopes called the Event Horizon Telescope, we captured the first ever direct image. A glowing ring of superheated gas circling the abyss, the silhouette of a black hole in the galaxy M87. This central engine is not just a passive anchor. Its immense gravity and magnetic fields act as a cosmic regulator, influencing the birth of stars throughout the entire galaxy. It can spew out colossal jets of energy that travel for thousands of light years, heating up galactic gas and quenching star formation. Or, its gravitational pull can shepherd gas into dense nurseries where new suns ignite. Radiating out from this central darkness is the galactic bulge, a tightly packed sphere of older, redder stars. Beyond this lies the main spectacle, the spiral arms, sweeping bands of dust, gas, and brilliant young blue stars. These arms are not solid structures like the blades of a pinwheel. They are density waves, cosmic traffic jams, moving slowly through the galactic disk. As clouds of interstellar gas and dust drift into one of these high-density waves, they get squeezed. This compression is the trigger. Gravity takes over, pulling the gas into tighter and tighter clumps, until the pressure and temperature at their cores become so extreme that nuclear fusion ignites. A star is born. These nebulae, these stellar nurseries like the famous pillars of creation, are where the raw materials of the cosmos are forged into luminous beacons. Our own sun was born in such a nursery 4.5 billion years ago, and it is within the fiery hearts of these stars, and in the explosive supernovae of their deaths, that heavier elements are created. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of it was cooked in a stellar furnace, in a star that lived and died long ago, inside a galaxy that is just one of trillions. But everything we have described so far, the black holes, the nebulae, the 200 billion stars of our galaxy, the 2 trillion galaxies themselves, all of this visible matter constitutes a shockingly small fraction of what is actually out there. All the light, all the beauty, all the substance we can see and measure amounts to less than 5% of the total mass and energy of the universe. The rest, the overwhelming majority of reality, is hidden. It is composed of 2 substances that we have named, but whose nature remains one of the most profound mysteries in all of science. They are dark matter and dark energy. The first clue to this invisible reality came not from a powerful telescope, but from the meticulous work of an astronomer named Vera Rubin in the 1970s. She was studying the rotation of galaxies, measuring the speed of stars at various distances from the galactic center. Physics predicted a simple outcome. Just as planets farther from our sun move more slowly, stars at the outer edge of a galaxy should travel at a much slower pace than those near the core, where most of the visible mass is concentrated. Rubin's observations revealed the exact opposite. The stars on the galactic fringe were moving just as fast as the stars in the middle. In fact, they were moving so fast that the gravity from all the visible stars and gas shouldn't be nearly enough to hold them in their orbits. The galaxies should be flying apart, flinging their stars into the intergalactic void, but they weren't. Something else was there, something invisible, something with immense gravitational pull was holding these galaxies together. This unseen substance was dubbed dark matter. Imagine a grand carousel at night, illuminated by beautiful, bright lights. You can watch the lights spin, and from their speed, you can calculate how much the carousel structure must weigh. Now, imagine the carousel starts spinning faster and faster, at a speed so reckless the lights should be torn from their mountings and sent flying, yet they remain perfectly in place. You would have to conclude that there are invisible, heavy chains connecting every light to the central pillar, providing the extra grip needed to prevent a catastrophe. Dark matter is those invisible chains. It is a vast, spherical halo of material that surrounds every galaxy, enveloping it in an unseen gravitational embrace. We can't see it. It doesn't emit light, reflect light, or interact with ordinary matter in any way we can detect, except through its gravity. Scientists all over the world are now engaged in a modern-day quest for the Holy Grail, to directly detect a particle of this ethereal substance. In deep underground laboratories, shielded from cosmic rays by kilometers of solid rock, physicists have built ultra-sensitive detectors. They are hoping to catch the faintest whisper of a dark matter particle bumping into an atom of their detector material. So far, there has only been silence. Yet, we know it must be there. Our models of the universe depend on it. This dark matter isn't just a minor addition to the cosmic inventory. It outweighs all the normal matter, all the stars, planets, and gas by a factor of more than 5 to 1. It is the true scaffolding of the cosmos. The trillions of galaxies we see are merely the luminous foam, the bright decorations hung upon a vast, invisible architecture of dark matter. If the discovery of dark matter was shocking, the discovery of the universe's other great secret was utterly bewildering. For most of the 20th century, cosmology was dominated by one central question: what is the ultimate fate of the universe? The Big Bang set everything in motion, flinging all the galaxies outward. The force of gravity, however, acts as a cosmic brake, pulling everything back together. The fate of the universe depended on which force would win. Would gravity eventually halt the expansion and cause the cosmos to collapse back on itself in a big crunch? Or would the expansion continue forever, with galaxies coasting apart into a cold, dark eternity? In the late 1990s, two separate teams of astronomers set out to answer this question. They used the same technique Hubble had, searching for standard candles in distant galaxies. This time, they used a different kind of candle, a type Ia supernova. These are the thermonuclear explosions of white dwarf stars, and they all detonate with almost exactly the same peak brightness, making them perfect for measuring cosmic distances. The teams observed dozens of these explosions in galaxies billions of light-years away. Their goal was to measure the rate at which the universe's expansion was slowing down. But when they analyzed their data, they found something that couldn't be right. It was so impossible. They spent months checking and rechecking for errors. There were no errors. The data was unequivocal. The expansion of the universe was not slowing down. It was speeding up. This was a discovery that shattered the foundations of cosmology. It was like throwing a set of keys into the air and watching them, instead of slowing down and falling back, suddenly accelerate upwards and shoot into the sky. Some unknown force, some form of anti-gravity, was actively pushing the fabric of space-time apart, overwhelming the pull of gravity on the largest scales. This mysterious influence was named dark energy, and when we calculate how much of this energy is needed to explain the accelerating expansion, the number is astounding. Dark energy appears to make up nearly 70% of the entire energy density of the cosmos. Think about that. Everything we know and understand, our planet, our sun, our galaxy, all 2 trillion galaxies, and even the enigmatic dark matter that holds them together, all of it combined is just 30% of reality. The dominant force in the universe is a phantom pressure, inherent in the vacuum of space itself, that is driving everything apart at an ever-increasing rate. We have no idea what it is. It is the single greatest puzzle in all of physics. This new, more complete picture of our universe reveals a structure of breathtaking beauty and scale. On the largest scales, galaxies are not scattered randomly like seeds in a field. They are organized by the invisible hand of dark matter and pushed apart by the relentless force of dark energy. Computer simulations show that the dark matter scaffolding has formed a colossal, spiderweb-like structure that spans the entire observable universe. It is known as the cosmic web. Immense, long filaments of dark matter, thousands of galaxies thick, stretch for hundreds of millions of light-years. Where these filaments intersect, they form massive superclusters, the great megacities of the cosmos, containing thousands of galaxies locked in a gravitational dance. And in between this luminous network are the great voids, cosmic deserts, hundreds of millions of light-years across, almost entirely empty of both dark and normal matter. Our Milky Way galaxy is located on a minor filament, on the outskirts of the Virgo supercluster, which itself is part of an even larger structure called Laniakea. Our real address is not a planet, or a solar system, or even a galaxy. It is a tiny, glowing node in an infinite, invisible web. This is our real universe. A cosmos of 2 trillion galaxies built on a scaffold of dark matter 5 times more massive, all being pushed apart by a mysterious dark energy that constitutes the bulk of reality. This understanding carries with it a profound and somewhat unsettling philosophical implication for the future. Because the expansion is accelerating, galaxies are not just moving away from us, they are moving away at an ever-increasing speed. Galaxies that are already very distant will eventually be receding from us faster than the speed of light. This doesn't violate Einstein's theory of relativity, because it is the fabric of space itself that is expanding. The light from those galaxies will be stretched so much it will never be able to cross the expanding gulf of space-time to reach us. They will, in effect, disappear beyond our cosmic horizon. One by one, the distant galaxies will blink out of our sight. If we wait long enough, billions upon billions of years, any future civilization in our local group of galaxies will look up at the night sky and see almost nothing. They will see the stars of their own merged supergalaxy, but the sky beyond will be black, empty, void. They will have no observational evidence that the other trillions of galaxies ever existed. They might develop a cosmology that concludes, as our ancestors once did, that they live in a single, solitary island universe. The full, glorious, and complex truth of the cosmos will have been erased by the expansion of space itself. We may be living in a uniquely privileged moment in cosmic history, a fleeting window of time where the universe is old enough to have created us, but young enough that we can still see back to the dawn of creation and witness the full grandeur of the 2 trillion galaxies. We have awoken on the shore of a cosmic ocean, and for a brief moment, we are able to see the distant continents before the tide of dark energy pulls them away forever. The truth behind the trillions of galaxies is not just a number, it is a new Copernican revolution. It is the ultimate realization that we are not special. Our planet, our sun, our galaxy, even our entire type of matter is a vanishingly small fraction of a much larger, stranger, and mostly invisible reality. But in that realization lies not a sense of insignificance, but a feeling of profound connection. The atoms that make up our bodies were forged in the heart of a star that died to seed the cosmos with the ingredients for life. The galaxy we inhabit is a testament to the organizing power of an unseen substance we are only just beginning to grasp. And the universe that surrounds us is a dynamic, evolving entity whose ultimate destiny is written in a force we cannot yet comprehend. The journey upward, which began with a simple glance at the stars, has led us here, to the edge of understanding, staring into a vast, dark, and magnificent reality with more questions than answers. And the desire to keep asking them is, perhaps, the most wondrous thing in the universe of all. What if the silent, unforgiving vacuum of space is not truly silent? What if the grand, cold emptiness we see between the stars holds the frozen echo of a sound made billions of years ago? It is a notion that defies our most basic experience. Sound as we know it needs a medium air water solid ground, something to carry its vibrations from a source to a receiver. In the near-perfect void of interstellar and intergalactic space, a scream, a whisper, an explosion all die before they are born. And yet we're here to tell you that this cosmic silence is a deception. It is the quiet of a concert hall after the final note has faded, leaving behind only a profound ringing memory. The universe you see was not always empty and cold. It was born in an unimaginable furnace of energy and matter, a state so dense, so utterly compressed, that it behaved not like the cosmos we know, but like the core of a star expanded to encompass all of reality. In this primordial state, a symphony of creation was playing out, and it was anything but silent. There was a sound, a single, universe-spanning pressure wave, a resonant hum that pulsed through the very fabric of existence. We cannot hear it with our ears, not anymore. But we can see its ghost. We can measure its imprint. This is the story of that sound, the first sound. It is the story of how its ancient fossilized echo has become our most powerful tool for understanding the cosmos, a celestial yardstick left behind by the Big Bang itself. This is the story of the baryon acoustic oscillations, and it begins not with a bang, but with a breath. To comprehend this primordial sound, you must first unlearn the universe, forget the galaxies flung apart like handfuls of diamonds on black velvet, forget the stars, the planets, the asteroids, the dust. Forget even the atoms that make up your own body. We must travel back to a time before any of these things existed to the universe's infancy, a mere 300,000 years after the moment of creation. In this era, there was no darkness, only an inescapable uniform light. The entire cosmos was a seething, opaque fog of plasma, a quantum soup of fundamental particles. Protons, the hearts of future atoms, jostled against electrons, their energetic dance partners, and surging through it all was a relentless flood of photons, particles of light so energetic and so numerous that they acted like a physical substance, a tangible force. This was a universe where matter and light were shackled together, locked in a gravitational cradle. Imagine a substance 1,000,000,000 times denser than water heated to a temperature hotter than the surface of any star, filling every conceivable point in space. This was our universe, a luminous, high-pressure prison. Within this cosmic plasma, two colossal forces were locked in a war that would determine the fate of all future structure. On one side was a force you know intimately: gravity. The immense collective gravity of all the particles in the plasma was a shepherd relentlessly trying to herd matter together. Any region that was by sheer chance infinitesimally denser than its surroundings became a gravitational seed, a cosmic basin pulling more and more material in. Gravity's voice in this symphony was the deep, undeniable bass note, the percussive beat, pulling everything towards a crescendo of collapse. It was the force of clumping, of gathering, of building. It wanted to sculpt the smooth, uniform plasma into mountains and valleys, the future cradles of galaxies and clusters of galaxies. It was the architect of cosmic destiny, drawing the first faint blueprints for the celestial cities we see today. This relentless inward pull was the inhalation of the young universe. But gravity was not unopposed. For every action there is an equal and opposite reaction, a truth as applicable to the primordial cosmos as it is to our world. The opposing force was the plasma itself, specifically the photons trapped within it, a force we call radiation pressure. As gravity squeezed a region of plasma, making it hotter and denser, the photons trapped inside fought back with ferocious energy. This photonic storm, this celestial blowtorch, generated an immense outward pressure, a repulsive force that violently resisted gravity's embrace. If gravity was the deep resonant bass note, then radiation pressure was the soaring defiant brass section, blasting outwards, determined to smooth out any imperfection, to silence any gravitational pull. This titanic struggle between the inward crush of gravity and the outward blast of radiation pressure was the engine of cosmic sound. It was the universe breathing, in and out. Gravity would gather a cloud of baryonic matter, the protons and electrons and the mysterious invisible dark matter that accompanied it. As the cloud compressed, the pressure and temperature would skyrocket until the trapped light exerted a force so great it overwhelmed gravity. The cloud would then explode outwards, a spherical shockwave of matter and energy rippling through the surrounding plasma. This was the sound wave, a baryon acoustic oscillation. It was not a wave travelling through air, but a wave of density itself, a pulse of reality propagating through the cosmic fluid. Think of it like dropping a stone into a perfectly still cosmic pond. From the point of impact, a slight overdensity of matter, a ripple expands outwards in a perfect circle. Now imagine this happening not on a two-dimensional pond, but in the three-dimensional space of the early universe. The ripple is not a circle, but a perfect sphere, a bubble of higher density expanding at incredible speed. The speed of this wave was immense, nearly 60% the speed of light, a testament to the extreme conditions of the primordial plasma. And these were not isolated events. They were happening everywhere. The entire universe was a churning, roaring sea of these sound waves, originating from every tiny fluctuation in density, crisscrossing and interfering with one another in a complex pattern of cosmic resonance. This was the symphony of the infant cosmos, a universe ringing like a bell struck a trillion times at once. This period of cosmic history was a battle, a dance, a song. The constant compression and rarefaction of the plasma, driven by the warring impulses of gravity and light, was the physical manifestation of sound. The universe was humming with a fundamental frequency, a note determined by the very properties of space and time itself. This celestial hum filled all of existence for hundreds of thousands of years. It was a process that was essential for our existence. Without this battle, gravity might have won, too quickly collapsing all matter into a universe of monstrous black holes, or radiation pressure might have dominated, smoothing everything out into a perfectly uniform, featureless and sterile cosmos. Instead, this acoustic oscillation, this cosmic breath, set the stage for a universe that was richly structured, lumpy and interesting enough to one day form stars, galaxies and us. The sound waves were sculpting the raw material of creation, carving out the voids and filaments that would become the large-scale structure of the universe we observe today. They were the vibrations that agitated the cosmic dust, allowing the first celestial sculptures to take shape. It was the most important sound you have never heard, but every song must end. Every symphony has its final fading chord. For the primordial sound of the universe, that moment came precisely 380,000 years after the Big Bang. It was a moment of profound, almost magical transformation known as recombination, or decoupling. Up to this point, the universe was so hot that electrons could not be captured by protons to form stable neutral atoms. Anytime an electron and proton got close, an energetic photon would slam into them, ripping them apart once more. This is why the universe was an opaque fog. Like particles, the photons were perpetually scattering off free electrons like car headlights in a dense mist, unable to travel any significant distance. They were trapped, and their entrapment fueled the outward pressure that drove the cosmic sound waves. But the universe, in its relentless expansion, was also cooling. Slowly and inexorably, the temperature of the cosmic plasma dropped. It finally crossed a critical threshold about 3,000 degrees Kelvin, roughly half the temperature of the surface of our Sun. At this temperature, the photons suddenly lacked the energy to break the bond between protons and electrons. All at once, across the entire cosmos, neutral hydrogen atoms formed. The electrons, once free-roaming agents of chaos, were captured, and with the electrons now bound into atoms, the photons were set free. The fog cleared. In a single, universe-altering instant, the cosmos became transparent. Light was decoupled from matter, free to stream across the vastness of space, unimpeded for the very first time. This ancient light, a baby picture of the universe, is what we now see as the cosmic microwave background radiation, the afterglow of creation. But this great liberation of light had another equally profound consequence. It silenced the music. The moment the photons were released, the radiation pressure that had been fighting against gravity vanished. The outward pushing force that drove the sound waves was instantly turned off. The war was over, and at that precise moment, the spherical ripples of density, the baryon acoustic oscillations that had been travelling outwards for 380,000 years simply stopped. They froze in place. Imagine that stone dropped in the cosmic pond. Imagine the ripple expanding outwards, and then imagine the entire pond instantly freezing into solid ice. The ripple would be flash frozen, a permanent circular scar in the ice, marking the exact distance the wave had travelled before the world changed. This is precisely what happened to the primordial sound waves. The expanding shells of baryonic matter, that slightly denser sphere at the edge of the sound bubble, came to a screeching halt. They were left stranded their journey over a phantom ripple imprinted upon the very structure of the cosmos. The sound wave, a dynamic moving thing, had become a static ghostly object. A fossil, an echo made of matter. The sound itself was gone, but the shape of the sound, its wavelength, was now permanently etched into the distribution of matter throughout the universe. This frozen ripple had a very specific size. We can calculate it based on the physics of the early universe, how fast the wave travelled and for how long. The distance from the centre of the original overdensity to the edge of this frozen shell of matter is about 500 million light-years. It is a colossal, almost incomprehensible scale. But it is a known scale, a predictable size. It is a standard length, a cosmic measuring stick forged in the fires of the Big Bang and stamped all over the sky. This is the heart of our story. This is the revelation that has transformed modern cosmology. That ancient sound, which died more than 13 billion years ago, did not vanish without a trace. It left behind a ruler of astonishing precision. So how do we find this ruler today in a universe so vastly different from the primordial plasma of its birth? The original overdensity at the centre of the ripple and the shell of matter in the frozen wave, 500 million light-years away, were both seeds of structure. They were regions with slightly more matter than their surroundings, and with the outward pressure of light gone, gravity could finally and decisively take command. Over billions of years, gravity worked on these initial imperfections. The central clump pulled in more and more matter, eventually forming a galaxy, or more likely a massive cluster of galaxies. Simultaneously, the matter in the spherical shell also began to clump together, pulled by its own gravity, forming other galaxies and clusters. The result is a subtle but statistically undeniable cosmic preference. If you pick any galaxy in the sky and begin to map its neighbours, you will find a slight excess, a tiny but measurable bump in the numbers of other galaxies located at a distance of about 500 million light-years. It's as if every galaxy is the faint echo of the initial sound, and it is surrounded by a ghostly sphere of its brethren, marking the place where the primordial sound wave finally froze. This preferred separation, this characteristic distance between galaxies, is the baryon acoustic oscillation signature. It is the universe's fundamental wavelength writ large in the language of galaxies. Finding it is not easy. It requires mapping the precise three-dimensional positions of hundreds of thousands, even millions of galaxies across vast swathes of the sky. It is a monumental task of celestial cartography, pushing our telescopes and our technology to their absolute limits. We must look deep into the past, charting the cosmic architecture as it was billions of years ago. But by measuring this subtle pattern, this faint gravitational echo of a long-dead sound, we gain access to the universe's own measuring tape. Because we know the true physical size of this bioruler, that 500 million light-year distance determined by primordial physics, we can use it to measure the universe itself. By looking at distant galaxies, we see the ruler as it was in the distant past. We can measure how large it appears to us in the sky. Comparing its apparent size to its known true size allows us to calculate with stunning precision its distance from us and the rate at which the universe was expanding at that time. By doing this for galaxies at different distances at different cosmic epochs, we can piece together a history of cosmic expansion, a biography of the universe from its adolescence to its present day. And this is where our journey truly begins, because when we use this ancient ruler to survey our cosmos, we uncover a profound and disturbing mystery. Our map of cosmic history reveals that some 5 billion years ago, something began to push back against gravity. A strange unknown energy started to accelerate the expansion of the universe, driving galaxies apart at an ever-increasing rate. We call it dark energy, but giving it a name does not mean we understand it. It is the single greatest enigma in all of science, a phantom force that now dominates our universe and will dictate its ultimate fate. How do we hunt for something we cannot see, cannot touch, and cannot explain? We must follow the echoes of the universe's first breath. We must use the sound of the Big Bang as our guide, allowing its ancient frozen ripples to reveal the hidden nature of the cosmic darkness. The key to the future of our universe is written in its oldest echo. What is the truest measure of a universe? Is it the span of a human life, a fleeting spark against the backdrop of eternity? Or is it something grander, a unit of distance so immense it forces us to confront our own cosmic insignificance? For nearly all of human history, the heavens were a painted ceiling, a dome of inscrutable glittering points. We could chart their movements, predict their cycles, but their true distance, their unimaginable scale remained locked away, a secret whispered between the stars. The question of how far was not merely a technical problem, it was a philosophical barrier, a wall that defined the limits of our reality. To breach it, to survey the cosmos, as a cartographer maps a continent, would require a new kind of vision, a new kind of yardstick. It would ignite a quest that would span generations, push technology to its breaking point, and ultimately shatter our entire understanding of the universe's past, present, and ultimate destiny. This is the story of that quest. It's the story of a search for a reliable cosmic ruler, a search that would lead us from the flickering of nearby stars to the cataclysmic death of distant suns, and from there into a profound and unsettling mystery. It's a journey that reveals how the simple act of measuring distance could force us to rewrite the laws of physics and confront the existence of a ghost in the machine of the cosmos, a phantom energy that is at this very moment pulling everything apart. Our first tentative steps in this grand survey began with a simple geometric trick, one you can perform right now. Hold your thumb out at arm's length and close one eye, then the other. Your thumb appears to jump against the distant background. This is parallax, and for centuries it was our only tool. By measuring the tiny shift in a nearby star's position, as the Earth orbits the Sun, astronomers could triangulate its distance. But this celestial surveyor's tool has a cripplingly short reach. Beyond a few hundred light years, the shift becomes too minuscule to detect. and the vast majority of our own galaxy, let alone the billion galaxies beyond it, remained uncharted territory. The cosmic ocean was still immeasurably deep, and we were confined to its shallowest shores. We needed more than a ruler. We needed a lighthouse, a beacon of known brightness whose light could travel across unimaginable voids and still be seen. We needed something whose intrinsic luminosity was as fixed and reliable as a law of nature. We needed a standard candle. The breakthrough came not from a celebrated professor at a grand observatory, but from a quiet, meticulous woman working for little pay and less recognition at Harvard College Observatory. In the early 1900s, Henrietta Swan Leavitt was one of the Harvard computers, a team of women tasked with the laborious job of cataloguing stars from photographic plates. While studying a class of pulsating stars called Cepheid variables in the Magellanic Clouds, she noticed something extraordinary, a hidden pattern in their behaviour. The brightest Cepheids took the longest to complete their cycle of brightening and dimming. The fainter ones pulsed more rapidly. She had discovered a direct, unwavering relationship between their period and their absolute brightness. This was the key, the cosmic Rosetta Stone. Imagine a street lined with identical 100-watt light bulbs. The one closest to you appears brightest, and the ones farther away appear progressively dimmer. Because you know they all have the same wattage, you can precisely calculate their distance, based purely on how bright they appear. Leavitt's discovery turned Cepheid variables into cosmic light bulbs. By measuring the rhythm of their pulse, we could know their true wattage. By comparing that to their apparent brightness in our sky, we could finally accurately measure their distance. It was this key that Edwin Hubble used in the 1920s to unlock the true nature of the universe. Pointing the colossal Hooker telescope at the fuzzy Andromeda Nebula, he hunted for these pulsating stars. When he found them, his calculations delivered a staggering verdict. Andromeda was not a cloud of gas within our own Milky Way. It was nearly 1 million light-years away, an entire island universe of stars, a galaxy in its own right. In a single stroke, the known universe expanded by a factor of infinity. The painted ceiling of the sky was smashed, revealing a cosmos populated by hundreds of billions of galaxies, each a swirl of countless suns stretching out into the abyss. Using Leavitt's cosmic yardstick, Hubble went further. He measured the distances to dozens of galaxies, and by analysing their light discovered they were almost all rushing away from us. And the farther away a galaxy was, the faster it was receding. The implication was profound, inescapable. The universe was not static. It was expanding, a single, four-dimensional cosmic event that had been unfolding for billions of years. We were living in the aftermath of a primordial explosion, a Big Bang. Hubble had laid the foundations of modern cosmology, all built upon the patient, brilliant work of a woman who gave us our first reliable way to measure the heavens. But even the mighty Cepheids have their limits. To chart the truly deep cosmos, to peer back across billions of years of cosmic history and read the story of the expansion itself. We needed a brighter candle, still a beacon so incandescent it could be seen from the very edge of the observable universe. We needed the most violent, most luminous events in existence, the death of a star. Not just any stellar death would do. The universe is filled with fireworks of varying brilliance. What cosmologists needed was a very specific kind of explosion, one so uniform, so precisely calibrated by the laws of physics, that each one went off with almost exactly the same explosive yield and the same peak brightness. They found it in a cataclysm known as a supernova. The story of this cosmic bomb begins with a dead star, a white dwarf. This is the smouldering, super-dense cinder of a sun like our own, its nuclear fuel exhausted. But if this white dwarf is not alone, if it is locked in a gravitational dance with a companion star, a sinister process begins. Its immense gravity starts to siphon material, usually hydrogen and helium, from its larger neighbour. For millions of years, the white dwarf pulls this stolen matter onto its surface, accreting it layer by layer, growing heavier and more compressed. It is a ticking time bomb, and the fuse is a very specific number in physics, the Chandrasekhar limit, approximately 1.44 times the mass of our Sun. This is the absolute maximum mass a white dwarf can sustain before its own gravity overwhelms the forces holding it together. Once it crosses that threshold, the star collapses inward, triggering a runaway thermonuclear reaction. In an instant, the entire star detonates in a blast of unimaginable power, a fusion bomb the size of a planet. For a few brilliant weeks, this single exploding star can outshine its entire host galaxy of billions of stars. Because they all explode at the exact same critical mass, they all release a near identical amount of energy. They were perfect. They were the ultimate standard candles. By the late 1990s, two competing teams of astronomers embarked on an epic hunt for these ephemeral beacons in the most distant galaxies they could find. The Supernova Cosmology project, led by Saul Perlmutter, and the High Z Supernova search team, co-founded by Brian Schmidt and Adam Rees, were engaged in a fierce but friendly rivalry. Their mission was clear, their goal seemingly straightforward. They sought to measure the history of cosmic expansion. For decades, the prevailing wisdom was that the expansion, while ongoing, must be slowing down. Gravity, the great cosmic break, is woven into the fabric of the universe. Every galaxy, every star, every particle of dust is constantly pulling on every other. This mutual attraction should act as a drag on the initial impulse of the Big Bang, gradually causing the expansion to decelerate. The only real question was by how much? Was there enough matter in the universe to eventually halt the expansion and cause a big crunch, a cosmic collapse back into a singularity? Or would the universe expand forever, but at an ever-slowing rate, fading into a cold, dark and empty future? The supernovae held the answer. By finding dozens of these explosions at various distances and therefore at various points back in cosmic time, the teams could plot the expansion rate throughout history. They were not just taking a snapshot, they were making a movie of the universe's life. The work was a monumental exercise in patience and precision. Month after month, they would survey patches of the night sky with powerful telescopes, taking images of tens of thousands of galaxies. Then, a few weeks later, they would image the exact same patches again. The real work was in the comparison, digitally subtracting one image from the other to see if any new points of light had appeared. Most of the time, there was nothing. But every so often, a new star would flare into existence where none had been before a supernova caught in the act billions of light years from home. Once a candidate was found, a frantic race against time began. They had to use the world's largest telescopes to get a spectrum of the light before it faded, confirming it was indeed a type Ia and precisely measuring how much its light had been stretched or redshifted by the expansion of the universe. This redshift gave them its recession velocity. The apparent brightness of the supernova gave them its distance. By plotting one against the other for dozens of supernovae, the cosmic history book would be opened. Both teams worked for years, meticulously collecting their data points, building their respective cases. As the plots began to take shape, a sense of confusion and then astonishment began to creep into their analysis. Something was deeply, fundamentally wrong. The most distant supernovae, the ones that showed us the universe as it was 5, 6, 7 billion years ago, were consistently dimmer than they should have been. A dimmer candle means only one thing: it is farther away than you thought. For the supernovae to be farther away than predicted by the standard model of a decelerating universe, the expansion of space could not have been slowing down over the last several billion years. It had to have been doing the exact opposite. It had to be speeding up. The universe was not just expanding, it was accelerating. Imagine throwing a ball into the air. You expect gravity to slow it down to see it rise more and more slowly until it stops and falls back to Earth. Now imagine throwing that ball, and instead of slowing it, rockets away from you faster and faster into the sky. This is what the supernova data was screaming. It was a result so bizarre, so contrary to all expectation, that both teams spent the better part of a year trying to find a mistake. They checked for systematic errors. Could intergalactic dust be obscuring the light, making the supernovae appear dimmer than they truly were? Plausible, but the effect would be different for different colours of light, a signature they didn't see. Could the supernovae in the early universe have been chemically different, intrinsically fainter than their modern counterparts? Perhaps, but there was no evidence to support it. Every alternative they explored led to a dead end. The data was ruthless in its consistency. The conclusion, however unbelievable, was inescapable. In 1998, the two teams presented their findings and the world of cosmology was thrown into chaos. The discovery of an accelerating universe was a thunderclap. It meant that the cosmos was not dominated by the gravitational pull of matter as we had always believed. Instead, some other entity, some bizarre anti-gravitational force must be at play. This mysterious influence, which seems to be woven into the very fabric of space itself, was pushing the universe apart. It was given a name, though the name did little to dispel the mystery dark energy. It accounts for nearly 70% of the total energy density of the cosmos. Yet we have no idea what it is. It is a ghost in the machine, a repulsive force that grows stronger as the universe expands a runaway cosmic engine, driving galaxies apart at an ever-increasing pace, propelling us toward a future of profound isolation, a big rip, or a big freeze. This discovery, which would rightly earn its leaders the Nobel Prize, was one of the most significant in the history of science. But extraordinary claims demand extraordinary evidence. The entire edifice of accelerating expansion and dark energy was built on the foundation of Type Ia supernovae. As brilliant as they were they truly infallible? Were we being tricked by some subtle astrophysical nuance of exploding stars we didn't yet understand? Science could not rest on a single pillar, no matter how strong it seemed. To truly believe in this strange runaway cosmos, we needed a second opinion. We needed a completely independent method for measuring the universe, a new cosmic ruler forged, not in the hearts of dying stars, but in the fires of the Big Bang itself. To find this new ruler, we must embark on a journey far beyond the reach of any telescope that sees in stars and galaxies. We have to rewind the cosmic clock back past the formation of the first stars, past the era of the first atoms, back to a time when the entire observable universe was a place of unimaginable heat and density. We must go to the beginning. For the first 380,000 years after the Big Bang, the universe was not the dark transparent void we know today. It was an opaque, searingly hot and impossibly dense plasma, a seething cosmic soup 1 billion times hotter than the surface of the sun. In this primordial furnace, nothing familiar could exist. There were no atoms, no molecules, no stars, no planets. The universe was a frantic storm of fundamental particles. There were the photons, the particles of light carrying immense energy. There were electrons unbound and free-roaming. And there were the baryons, the particles that would one day form all the protons and neutrons of every atom you have ever touched. These three components, photons, electrons and baryons, were locked together in an intimate, violent dance. The photons were so energetic they would instantly blast apart any atom that tried to form, keeping the electrons and baryons separate in a charged ionized fluid. In this state, the universe was like a thick glowing fog. A photon couldn't travel more than a few inches without slamming into a free electron, scattering it in a new direction. The cosmos was utterly opaque. But this primordial soup had another crucial ingredient, a silent, invisible character that was already shaping the universe's destiny. This was dark matter. While the photons and baryons were furiously interacting, crashing into each other, trillions of times a second, the particles of dark matter drifted through the chaos completely untouched. They did not feel the electromagnetic force, so they did not see the photons. They felt only gravity. And because they made up the vast majority of the matter in the early universe, their gravity was the dominant force. From the very first moments, dark matter began to clump together, forming vast invisible halos, gravitational wells that would one day become the seeds of galaxies. As these dark matter halos grew, their immense gravity began to pull on the incandescent plasma surrounding them. The photon-baryon fluid, this glowing fog of normal matter and light, felt the pull. It began to fall into these deep gravitational wells created by the dark matter. But as it became compressed and heated, the photons trapped within, it began to fight back. Their immense radiation pressure created a powerful outward force, resisting the crush of gravity. Here in the cradle of the cosmos, two colossal forces were pitted against each other, the relentless inward pull of gravity from dark matter and the explosive outward push of light itself. A tension was building in the fabric of the infant universe. The stage was set for something spectacular. A wave of pressure was about to be unleashed, a sound wave of cosmic proportions, a ripple in the primordial fluid that would forever change the shape of everything to come. And so, we find ourselves suspended in a moment of profound cosmic infancy, less than a few 100,000 years after time itself began. The universe we were born into with its cold voids and glittering islands of light does not yet exist. In its place is a spectacle of unimaginable power, a realm not of stars or galaxies, but of pure, unbridled potential. Before us lies the primordial furnace, a state of matter so extreme, so alien, that our modern physics can only barely grasp its character. It is a seething incandescent fog, a cosmic fluid composed of every fundamental particle that will ever exist, all crushed together under impossible pressures and heated to temperatures thousands of times hotter than the surface of our sun. This is the baryon photon plasma, and within its chaotic depths, a battle of titans is about to commence, a conflict whose outcome will write the future story of structure of galaxies, of worlds, and of us. At the heart of this conflict are two opposing yet fundamental forces of nature. On one side, you have the most familiar force of all gravity. But this is not the gentle gravity that holds you to your chair. This is gravity in its most primal, most ambitious form. In this dense cosmic soup, tiny, almost imperceptible fluctuations in density exist echoes of an even earlier quantum era. These are the seeds. The slightly denser regions, dominated by the mysterious invisible scaffolding of dark matter, possess an ever so slightly stronger gravitational pull. Relentlessly, inexorably, these gravitational wells begin to draw the surrounding plasma inward. They are cosmic anchors patiently tugging on the fabric of the universe, seeking to gather matter to collapse it to begin the long, slow process of building the first great structures. This is gravity's imperative to clump, to collect, to create. Every particle of normal matter, every proton and neutron, what we call the baryons, feels this irresistible summons, a siren song pulling them toward a shared compact destiny. But for every action, there is a reaction. And in this primordial cauldron, gravity does not act alone. Opposing it is a force of truly stupendous power, radiation pressure. You see, the plasma isn't just a thick soup of matter, it is blindingly, furiously bright. It's a universe saturated with photons, particles of light so energetic and so numerous that they behave less like light and more like a physical substance, a powerful, incompressible fluid of pure energy. These photons are not free to travel. They're trapped in a cosmic pinball machine, constantly scattering off the free-floating electrons, unable to move more than a minuscule distance before colliding with another particle. This constant violent scattering creates a staggering outward pressure, a celestial blowtorch pushing against gravity's pull. So as gravity tries to squeeze a clump of plasma, it simultaneously squeezes this ocean of trapped light. The more the plasma compresses, the hotter and denser the photons become, and the more furiously they push back, resisting collapse with all the might of the universe's nascent energy. Here in this cosmic crucible is the ultimate stalemate. An overdense region of dark matter begins its slow gravitational work, pulling the baryons and their coupled photons inward. For thousands of years, the clump grows, compressing under its own weight, becoming hotter and denser, a glowing jewel of potential in the primordial fog. But as it compresses, the photon pressure within it builds, mounting a furious defense. It rises and rises until it becomes overwhelming, a repulsive force that gravity can no longer contain. At a critical point, the tables turn. The inward fall of matter is halted and then dramatically reversed. The immense pressure of the trapped light erupts, driving the plasma outward in a spherical, expanding shell. The compression gives way to rarefaction. The clump of matter which had been gathering for millennia is now blasted apart by its own internal energy. This is not merely an explosion, it is something far more fundamental, far more rhythmic. It is the first note in a symphony that will fill the entire cosmos. It is the birth of a sound wave. Of course, this wasn't sound as you and I would recognize it. There was no air to carry a vibration, no ear to hear it. This was a wave of a far grander scale, a physical oscillation of density and pressure, propagating not through air, but through the very substance of the infant universe. Imagine dropping a stone into a perfectly still pond. Ripples expand outwards in perfect circles. Now imagine this happening everywhere in the universe at once. Every single one of those initial slight overdensities acted as a stone dropped into the cosmic plasma at the same moment. From each point, a spherical wave of compression and rarefaction began to propagate outwards, travelling at a staggering velocity over half the speed of light. These were the baryon acoustic oscillations. For 380,000 years, the young universe was not a silent void. It was a roaring, thrumming, resonant cavity filled with the deep subsonic hum of these immense pressure waves. The entire cosmos was ringing like a bell struck by the Big Bang itself. These waves were the universe's first transportation system. Riding these expanding shells of pressure were the baryons, the raw material for all future stars, galaxies, and life. They were dragged along, bound inextricably to the photons whose pressure was driving the expansion. The two components, matter and light, moved as one, a single unified fluid dancing to the rhythm of gravity and pressure. The wavefront, an expanding sphere of slightly denser, hotter plasma, raced outwards from its point of origin, carrying the blueprint for future structures with it. Behind it, it left a region of lower density, the rarefied trough of the wave. All across the cosmos, this process was being repeated, creating an incredibly complex pattern of intersecting, interfering ripples. This was the universe in its most dynamic, most vibrant phase, a period where the fundamental laws of physics were engaged in a delicate yet universe-spanning choreography, a dance that would determine the distribution of all matter for the next 13 billion years. It was a beautiful, elegant, and perfectly balanced system, but like all perfect moments, it was destined not to last. The universe all this time was doing two things. It has never stopped doing. It was expanding and it was cooling. The relentless stretching of space-time was pulling everything apart, constantly working to dilute the density and sap the energy from that primordial furnace. For hundreds of thousands of years, the temperature dropped slowly, but surely from billions of degrees down to thousands. A critical threshold was approaching. The cosmic plasma, this chaotic union of matter and light, was on the verge of a profound, phase-changing transformation. The key to this change lay in the relationship between the protons and the electrons. In the intense heat of the early universe, they were simply too energetic to combine. Any electron that was captured by a proton was immediately blasted away by a high-energy photon. The universe was simply too hot for atoms to exist. But as the cosmic thermostat wound down, the photons became less energetic. The universe was getting calmer, less violent. It was approaching a tipping point, a magical temperature of around 3000 Kelvin, and then it happened. All across the cosmos, almost simultaneously, the universe cooled just enough. The energy of the average photon dropped below the level required to knock an electron away from a proton. Suddenly, capture was permanent. For the first time, stable neutral atoms could form. Protons and electrons, which had spent millennia as free-roaming independent particles, found their partners binding together to create the first atoms of hydrogen and helium. In a geological instant, a span of just a few thousand years, the entire universe underwent a cataclysmic change. The free electrons, which had been the primary obstacle for photons, were now locked away inside neutral atoms. The cosmic fog that had filled all of space for 380,000 years, the opaque plasma that had trapped light since the beginning of time, simply vanished. The universe, in a single glorious moment, became transparent. This event is what we call decoupling, or recombination. It was a great liberation. For the photons, this was a moment of release. No longer shackled to matter, no longer trapped in an endless series of collisions, they were suddenly free to travel in a straight line, unimpeded across the cosmos. The light that had been locked inside the plasma was now released in a brilliant flash, filling all of space. And this is not just a theoretical idea. We can still see this light today. Stretched by 13 billion years of cosmic expansion, cooled from a searing 3000 degrees to a mere 2.7 degrees above absolute zero, these ancient photons now arrive at our telescopes not as visible light, but as a faint uniform glow of microwaves coming from every direction in the sky. This is the cosmic microwave background. When we look at it, we are looking at the afterglow of creation, the oldest light in the universe, a fossilized photograph of the very moment the cosmos became transparent. It is a baby picture of our universe, and imprinted upon it are the faint hot and cold spots, left by those primordial sound waves at the exact moment they were frozen. But what of the baryons? What of the normal matter that had been riding these waves? For them, the moment of decoupling was one of profound abandonment. They were passengers on a wave powered by photon pressure. When the photons were set free, the engine of the wave simply shut off. The outward pressure that had been driving the expansion of the plasma shell vanished. The sound wave didn't fade away. It stalled, frozen in its tracks. Imagine that ripple on the pond again. But now imagine the pond instantly freezing solid. The ripple would be trapped a static circular ridge in the ice, a perfect record of the wave at the moment it stopped. This is precisely what happened in the universe. At the moment of decoupling, every single sound wave at whatever point it had reached in its 380,000-year journey was locked into place. The spherical shell of baryons which had been racing outwards was left stranded. It was no longer being pushed outwards by photons, and the gravitational pull from the central point of origin was now too weak to pull it back in. This left a truly remarkable signature, an ethereal ghost imprinted upon the very fabric of the cosmos. At the centre of where each wave began, there is a clump of matter, the baryons, that never managed to escape the initial gravitational well, and surrounding it at a very specific distance is a vast spherical shell containing a slightly higher than average density of other baryons, the crest of the sound wave frozen in place at the moment of liberation. The distance from the centre of the original clump to this outer shell is the same everywhere, because every wave travelled at the same speed for the same amount of time through the same medium. This fixed distance, this characteristic length scale, corresponds to how far a sound wave could travel in the 300,000 years before the universe became transparent. It works out to be a distance of about 490 million light-years in today's universe. It is a standard ruler bequeathed to us by the physics of the Big Bang. This process did not happen in just one place. It happened everywhere there was an initial overdensity. The universe was left with a subtle yet pervasive preference. If you picked any given clump of matter in the early universe, you would be slightly more likely to find another clump of matter located about 490 million light-years away from it. This is the echo of the sound of creation. For hundreds of millions of years, this faint ghostly imprint lay dormant in the distribution of hydrogen and helium gas that filled the dark, transparent cosmos. Gravity, now the uncontested ruler of cosmic evolution, began to work on this template. The overdense regions, both the central clumps and the vast shells of the frozen sound waves, slowly began to gather more and more matter. They were the fertile ground where the first stars would ignite and the first galaxies would begin to spin. The faint whisper of the Big Bang sound had become the blueprint for the cosmic web, the grand architecture of the universe we see today. The sound itself may have fallen silent 13 billion years ago, but its echo is written in the stars. The great challenge for astronomers then became a search for this echo. How could you possibly measure a ghost? How do you survey the cosmos on such immense scales to find a faint statistical preference in the spacing of galaxies, a preference left by a ripple in a long-vanished sea? The answer would require new technologies, new observatories, and a new way of mapping the heavens, a celestial cartography aimed at uncovering the faintest, most ancient music of the spheres. And so the echo was left behind, frozen in place, a ghostly sphere of slightly denser matter expanding outwards from every single overdensity in that primordial cosmic ocean, a final, silent testament to a sound no one could ever hear. For decades, this was where the story ended, a beautiful, elegant piece of theoretical physics, a prediction locked away in the mathematics of the cosmos, seemingly destined to remain forever beyond our grasp. Because how could we possibly hope to see it? 13 billion years of cosmic evolution stood between us and that fleeting moment of creation. The universe had expanded 1,000-fold since then. That delicate ephemeral ripple, once a microscopic feature, should now be a colossal structure, a ghostly ring nearly 500 million light-years in diameter. It was a scale so vast it defied all conventional astronomy. You could never point a telescope and simply see one. These were not rings of fire, but rings of probability. The sound wave's fading whisper was not written in light, but in the subtle, almost imperceptible placement of galaxies. The prediction was clear, yet impossibly demanding. It suggested that if you were to pick any galaxy in the sky, you would be just a tiny bit more likely to find another one at a distance of 500 million light-years than at 400 million or 600 million. That was it. A whisper-thin statistical preference, a cosmic inclination buried within the chaotic tapestry of the entire visible universe. To find it would be like trying to hear a single pin drop in the middle of a global hurricane from 1,000 miles away. It was a signal so faint, so drowned in the noise of gravity, that its detection seemed to require a map of everything, or at least a significant fraction of it. The challenge was no longer one of theory, but of industry, of brute force. It required a shift in the very philosophy of astronomy, moving away from the meticulous study of individual unique objects towards something far more ambitious, almost shockingly so. What was needed was a census, a grand cosmic survey of a scope never before attempted, a project that would chart the three-dimensional positions of not thousands, but hundreds of thousands, even millions of galaxies. It was a dream that bordered on technological fantasy, a monolithic task that would require new telescopes, new cameras, and an entirely new way of processing the torrent of data that such an endeavour would unleash. The old way of doing astronomy was simply not enough. An astronomer might spend an entire night on a powerful telescope to capture the spectrum of a single distant galaxy, painstakingly teasing out the secrets of its light. To find the baryon acoustic peak this way was a fool's errand. It would take not lifetimes, but millennia. A revolution was needed, and from the high deserts of New Mexico and the remote plains of Australia that revolution began. Two colossal projects born of the same indomitable ambition rose to meet this seemingly impossible challenge. They were the 2DF Galaxy Redshift Survey, or 2DF-GRS, and the project that would ultimately redefine the field, the Sloan Digital Sky Survey, or SDSS. These were not telescopes in the traditional sense. They were galaxy-devouring machines. At the Apache Point Observatory in New Mexico, the Sloan telescope was a marvel of focused efficiency. Its unique design allowed it to capture a huge swathe of the sky, 7 times the area of the full moon in a single snapshot. But its true genius lay not in its mirror, but in what came next. This was astronomy as a production line, a factory for the cosmos. The process began not with an eyepiece, but with a drill. For each patch of sky Sloan would observe, a team would engineer a circular aluminum plate, a precise mirror of the starfield it was about to study. Upon this plate, a high-precision robotic drill, guided by earlier imaging surveys, would bore hundreds of tiny holes. Each hole was an address, a specific targeted destination, marking the exact location of a galaxy or a quasar. These were not random points. They were a curated list of targets, a carefully selected population chosen to give the most representative slice of the universe possible. Then came the heart of the operation. In a clean room, technicians would undertake a task of almost unbelievable complexity and delicacy. They would take hundreds of individual optical fibers, each thinner than a human hair, and plug them by hand into the holes on the aluminum plate. Each fiber was a tiny private pipeline for ancient light. When the plate was mounted on the back of the telescope, each fiber would align perfectly with its target galaxy, siphoning off its faint travel-worn light and channeling it deep into the belly of the instrument. This was a celestial switchboard, a jacquard loom for the cosmos, weaving together the light of 1,000 galaxies simultaneously. That light, collected over an hour-long exposure, was then fed into a bank of spectrographs. These instruments acted like prisms on an industrial scale, breaking the light of every single galaxy into its constituent rainbow, its unique spectrum. And within that spectrum, astronomers could see the telltale shift of spectral lines towards the red end, the redshift, a direct measurement of how much the universe had expanded while that galaxy's light was travelling towards us, a direct measurement of its distance. Night after night, the process repeated with ruthless efficiency. A new plate for a new patch of sky, a new set of 1,000 galaxies meticulously catalogued. Meanwhile, half a world away at the Anglo-Australian telescope, a parallel effort was pushing the boundaries with different technology. The 2DF instrument employed a sophisticated robotic positioner, a marvel of engineering that could place 400 optical fibers onto a target field with astonishing speed and precision, eliminating the need for manually plugged plates. It was a race not of rivals but of collaborators in a shared quest, 2 titanic experiments chipping away at the cosmic map, each confirming the other's progress, each pushing the other forward. The data poured in. not as beautiful images, but as a relentless, overwhelming flood of numbers. Redshifts, coordinates, brightness levels, terabytes of raw information streamed from the mountaintops to data centers around the world. For the first time, we were not just looking at the universe, we were digitizing it. We were building a virtual cosmos inside our supercomputers, a vast three-dimensional model built not from theory, but from the light of 1 million individual real-world galaxies. As the map grew, its structure began to emerge from the noise. We saw the universe as it truly is on the larger scales. Not a random scattering of points, but a magnificent intricate structure often called the cosmic web. We could fly through great walls of galaxies, immense sheets of matter stretching for hundreds of millions of light years. We could plunge into the desolate voids, the vast empty deserts that lay between these colossal structures. We saw the wispy filaments connecting them, the great cosmic highways along which matter flows to feed the gargantuan galaxy clusters that sit like glittering cities at the intersections. It was a breathtaking confirmation of what simulations had predicted. The grand web-like structure sculpted by the invisible hand of dark matter and the relentless pull of gravity over billions of years. But this beautiful map, as revolutionary as it was still just the backdrop. The real prize, the sound of the Big Bang, was still hidden inside it, and finding it would require one final crucial step. The teams of scientists led by figures like Daniel Eisenstein and Sean Cole now faced the purely analytical part of the challenge. They had to interrogate this map to ask it a very specific question. They needed to compute something called the galaxy correlation function. The concept is elegantly simple, yet computationally monstrous. You tell the computer to pick a galaxy, any galaxy in the map. Then you ask it to count how many other galaxies exist in a thin spherical shell at a certain distance around it, say 10 million light-years away. Then you do it again for a shell 20 million light-years away, and again for 30 million, and so on out to billions of light-years. You repeat this process not once, but millions of times for every single galaxy in your survey, averaging the results together to wash out the local peculiarities and reveal the underlying cosmic truth. What you're searching for is a tiny blip, a slight statistical stickiness between galaxies. If the theory of baryon acoustic oscillations was correct, then as you moved your imaginary shell outwards from your central galaxy, the number of neighbouring galaxies should fall off smoothly, just as you'd expect from gravity's thinning influence. But then at one very specific distance, the size of that ancient sound horizon, stretched by cosmic expansion, there should be a bump. A small but unmistakable increase in the probability of finding another galaxy. It would be the ghostly echo of that primordial pressure wave, the faint collective gravitational memory of that initial cosmic ring. For years, the data accumulated. The maps grew denser. The computers at Fermilab and other institutions churned through the calculations, sifting through the positions of hundreds of thousands of galaxies. The noise was immense. Galaxies are pulled and tugged by local gravity, forming clusters and pairs that can easily mimic a signal. The motion of galaxies within those clusters can distort our measurements of their distance, an effect known as fingers of God, which had to be meticulously modelled and removed. The teams worked refining their techniques, expanding their datasets, pushing back the fog of statistical uncertainty. And then in 2005 it happened. Independently and with two different datasets, the SDSS and 2D-DFGRS teams saw it. There was no single flash of discovery, no dramatic shout of eureka. It was a slow creeping dawn of realization, as a curve on a computer plot began to resolve itself. As more and more data was added, the jagged, noisy line of the galaxy correlation function began to settle down. And there it was. Not a sharp spike, but a broad, gentle swell in the graph. A 1% excess of galaxy pairs centered right around a distance of 500 million light-years. It was almost disappointingly subtle to the untrained eye, a mere ripple on a vast statistical ocean. But to the cosmologists who had hunted for it, it was the roar of creation. It was the universe whispering its own history back to us. The sound wave, born in the first 380,000 years of time, had survived. It had weathered 13 billion years of relentless expansion. It had seeded the formation of galaxies, imprinting its memory onto their very locations in space. And now, through breathtaking ingenuity and tireless effort, we had finally built a map detailed enough a census vast enough to read that faint inscription. That single unassuming bump on a graph was one of the most profound discoveries in the history of science. It transformed cosmology overnight. The abstract concept of a standard ruler, something theorists had dreamed of, was suddenly real, tangible. We held it in our hands. It was as if the universe itself had provided a measuring stick, a colossal yardstick, of a known predictable length forged in the physics of the Big Bang and stamped across the sky. The hypothesis had been validated in spectacular fashion. The sound had been found. The real work, the work of using this extraordinary new tool, was about to begin. We now had a way to measure the universe, to survey its geometry on the grandest of scales. And with this ruler, we could finally hope to confront the greatest mystery of all, the strange accelerating expansion of space and the invisible, unknowable dark energy that drives it. The echo of the past was about to become our map to the future. And so, with this cosmic yardstick finally in our grasp, humanity stood at a profound turning point. The ethereal echo of a sound wave from the dawn of time had been calibrated, transformed from a theoretical marvel into a practical physical tool. We possessed a ruler of truly cosmological proportions, one whose length was not etched in metal or stone, but woven into the very fabric of space-time by the physics of the universe's first moments. The question that now consumed the minds of astronomers was no longer what it was, but what we could do with it. How could this ghost of a primordial sound, this subtle preference for galaxies to be separated by 500 million light-years, be wielded to write the biography of the universe itself? The task ahead was a challenge of almost unimaginable scale. It was to become cosmic cartographers, mapping not a continent or a planet, but the entire visible cosmos across billions of years of its own history. The goal was to create a three-dimensional map, a cosmic atlas so vast and so detailed that this faint statistical whisper of the ancient sound waves would become an audible signal. This meant looking out into the depths of space, which is also to look back into the depths of time, and to measure the apparent size of our standard ruler at different epochs. Imagine holding a coin of a known fixed size. If you see it nearby, it appears large in your field of view. If you see it from a mile away, it appears as a tiny speck. Because you know its true physical size, a simple measurement of its apparent size on your retina tells you its distance. The baryon acoustic oscillation peak is our cosmic coin. We know its true physical size with incredible precision, anchored by the exquisite measurements of the cosmic microwave background. It is a sphere of influence roughly 500 million light-years in diameter, stamped upon the cosmos at recombination. Now all we had to do was find the imprint of that sphere in the distribution of galaxies at different distances from us at different moments in cosmic history. By measuring how large that sphere appears on the sky at a given cosmic age, we could calculate the distance to that age with an accuracy that was previously unthinkable. Do this for galaxies 1 billion light-years away, then for galaxies 3 billion light-years away, then 5, then 7, then 10. By repeating this measurement over and over, stepping back through cosmic time, we could piece together a definitive history of how the universe has expanded. We could create the universe's growth chart. It sounds simple in principle, but the practice is a campaign of heroic, painstaking, and often frustrating effort. To even begin, you need a catalogue of galaxies, not thousands, not even hundreds of thousands, but millions, tens of millions, hundreds of millions. And you don't just need their position on the sky, their two celestial coordinates, like latitude and longitude on Earth. You need their third dimension, their distance, their depth. This is the crucial piece of information obtained by measuring a galaxy's redshift, the degree to which its light has been stretched to longer, redder wavelengths by the expansion of space. The greater the redshift, the farther away the galaxy is, and the further back in time we are seeing it. This monumental task of cosmic census-taking fell to a new generation of Leviathan telescopes and ambitious surveys. Projects like the Sloan Digital Sky Survey, or SDSS, revolutionized the field. From its perch in New Mexico, it began a methodical quest to map a quarter of the entire sky. Night after grueling night, the telescope would stare into the dark, not with a single camera, but with a custom-built instrument that could capture the light from hundreds of galaxies at once. At the telescope's focal plane was not a piece of film, but a meticulously crafted aluminum plate drilled with holes by a robotic arm, each hole corresponding to the precise location of a star or galaxy in that patch of sky. Human hands would then plug hundreds of individual optical fibres into these holes, a delicate, almost surgical procedure repeated for every new field of view. Each fibre acted as a tiny light pipe, channeling the faint ancient light from a single distant galaxy down into the belly of a spectrograph. There the light was split into its constituent colours, a rainbow or a barcode that revealed the galaxy's chemical composition, its age, and most importantly, its redshift. Over more than a decade, SDSS and its successors like the Baryon Oscillation Spectroscopic Survey, or BOSS, gathered spectra for millions upon millions of galaxies. The resulting database was not merely a picture book of the cosmos, it was a dynamic four-dimensional map of structure, a digital recreation of a vast slice of the universe. It was inside this colossal haystack of data that astronomers had to find the BAO needle. The challenge is that gravity itself makes galaxies cluster. Galaxies are not scattered randomly like dust motes in a sunbeam. They are caught in the invisible web of dark matter, drawn together into filaments, walls, and dense superclusters separated by immense barren voids. This gravitational clustering is the dominant symphony of cosmic structure. The BAO signal, by comparison, is a single faint note hidden within that overwhelming crescendo. It's not a bright ring of galaxies you can see with your eye. It is a subtle statistical overdensity. It is the universe whispering to us that for any given galaxy, there is a tiny, almost imperceptible increased probability of finding another galaxy 500 million light-years away. To hear this whisper, scientists employ a powerful statistical tool known as the two-point correlation function. It's a deceptively simple question posed to the vast cosmic map: pick a galaxy, any galaxy. Now, how does the number of neighbouring galaxies change as you look further and further away from it? You run this calculation not for one galaxy, but for millions, and you average the results together. At first, the function shows exactly what you'd expect from gravity, a huge number of neighbours very close by, which then drops off steeply as you move further away. But then as your search continues outwards through the lonely voids between clusters, something remarkable is supposed to happen. Right around that magic distance of 500 million light-years, the curve should briefly subtly rise again. A tiny bump in an otherwise smooth graph. That bump, that fractional percentage increase in the number of galaxy pairs, is everything. It is the echo of the Big Bang, the frozen crest of that primordial sound wave, finally revealing itself in the modern universe. The first tentative detections were electrifying, a triumph of decades of theoretical prediction and observational grit. But claiming a discovery of this magnitude required a level of scientific rigour that borders on obsession. The enemy of any such measurement is not a flaw in the theory, but a flaw in the observation, a hidden bias, a subtle error, what scientists call a systematic. These systematics are the ghosts in the machine of measurement, and they are terrifyingly easy to create. They are the nemesis of every observational cosmologist because they can create false patterns, or even worse, erase the very real subtle pattern you're trying to find. The litany of potential systematics is long and daunting. Perhaps the telescope's detector is slightly more sensitive on one side than the other, causing you to systematically find more faint galaxies in one direction, creating an artificial cluster. Perhaps a bright star in our own galaxy scatters light across the detector, making it harder to spot distant galaxies behind it, creating an artificial void. The Earth's own atmosphere, the very air we breathe, can subtly distort the starlight passing through it. Dust within our own Milky Way can absorb and redden the light from background galaxies, making them appear farther away than they truly are and shifting their perceived position on the map. Every single one of these effects and hundreds more must be hunted down, modelled, understood, and meticulously corrected for. The process is an excruciating exercise in self-doubt and cross-checking. Scientists spend years building complex computer simulations of the universe mock catalogues that are designed to look statistically identical to the real data. Into these simulations, they inject a known BAO signal of a specific strength. Then they degrade this perfect simulated data with all the known sources of noise and systematic error that plague the real telescope, simulated atmospheric distortion, simulated detector flaws, simulated galactic dust. The crucial test is then to run their analysis pipeline on this intentionally flawed simulated data. Can they still recover the original signal they put in? If they can't, their analysis is blind. If they recover a signal that is shifted or has the wrong size, they know their method is biased. Only when their tools can reliably and repeatedly extract the correct answer from these synthetic universes are they finally allowed to unleash them on the real precious hard-won data from the sky. It is a war fought not on a battlefield, but in lines of code, in statistical tests, and in endless debates over error budgets. And after all this struggle after the mapping, the measuring, the statistical sifting, and the relentless war against systematic error, the result that emerged was unambiguous and profound. When astronomers plotted the distance to each Bayer measurement against the redshift of the galaxies used, they built up point by painstaking point a history of cosmic expansion. The data told a story that was both expected and utterly shocking. In the distant past, for the first 7 to 8 billion years of cosmic history, the expansion was clearly slowing down. This made perfect sense. The universe is filled with matter and dark matter, all of which is gravitationally attractive. Like a ball thrown upwards from the Earth, the mutual gravitational pull of everything in the cosmos should be acting as a brake slowing the rate of expansion over time. The Bayer measurements from the distant universe confirmed this beautifully. But then as the data points crept closer to the present day, the trend reversed. Around 6 billion years ago, the universe stopped slowing down. The cosmic brakes began to fail, and then it started to speed up. The expansion of the universe began to accelerate. This was the smoking gun. The discovery of cosmic acceleration in the late 1990s using the light from distant exploding stars had been so bizarre, so contrary to all expectation, that it demanded independent verification. That verification had now arrived. The Bayer are a completely different physical phenomenon rooted in the sound waves of the infant cosmos, rather than the death of stars, was telling us the exact same incredible story. It was cosmology's checkmate. The evidence was overwhelming. Some mysterious repulsive force was at work in the cosmos, a dark energy that was pushing space itself apart, overpowering the collective gravity of all the matter within it. The BAO measurements not only confirmed its existence, they began to constrain its properties. They showed that this dark energy has been a significant component of the universe for billions of years, and that its influence has grown as the cosmos has expanded and the density of matter has been diluted. The cosmic ruler had not just measured the size of the universe, it had revealed the nature of its destiny, a future of ever faster runaway expansion. Yet as one great mystery was solidified into accepted fact, it opened the door to an even deeper one. What is this dark energy? Is it the cosmological constant that Einstein once proposed and later discarded, a constant energy density inherent to the vacuum of space itself? Or is it something even more exotic, a dynamic field that could change its strength over time, a quintessence that might one day fade away or even reverse its push into a cosmic pull? Answering this question requires pushing our cosmic ruler to its absolute limits. It requires measuring the expansion history with such exquisite precision that we can detect not just the acceleration itself, but whether that acceleration is constant or changing. This is the driving force behind the next generation of galaxy surveys, instruments of breathtaking ambition. The Dark Energy Spectroscopic Instrument, or DESI, is now at work mounted atop a telescope in Arizona. Instead of hundreds of optical fibers, it deploys 5,000 miniature robotic positioners that can pivot and stare at 5,000 individual galaxies simultaneously. In a single exposure, it can map more of the universe than its predecessors could in a month. Its goal is to create a map of over 35 million galaxies reaching back over 11 billion years in time. From space, the Euclid telescope, a mission by the European Space Agency, will chart an even larger volume of the sky immune to the blurring effects of Earth's atmosphere. And soon the Vera C. Rubin Observatory in Chile will begin its legacy survey of space and time, a project so vast it will image the entire southern sky every few nights, cataloguing not millions but billions of galaxies. These endeavours represent the next frontier. They are no longer just trying to detect the Bayer bump, They're designed to measure its position and shape with sub-percent precision across a dozen different slices of cosmic time. Each measurement will be another pin on the universe's growth chart, another test of our understanding of dark energy. The gentle statistical whisper of the Big Bang has become our most powerful tool for interrogating the deepest and darkest mystery of modern physics. The sound of creation is now the key to understanding our ultimate fate, a story whose next chapter is being written right now in the faint and ancient light of galaxies billions of light years away. And so, with our cosmic ruler finally in hand, we stand at a precipice. For millennia we gazed at the heavens and saw only disconnected points of light. We invented stories, drew heroes and monsters to impose order on the chaos. But to truly understand the cosmos, to write its biography, we needed more than a single story, more than one isolated clue. We needed to cross-examine our witnesses. The universe you see is a master of deception, a realm where different combinations of fundamental properties can conspire to produce what looks like the very same sky. This is the curse of cosmology, a problem known as degeneracy. Imagine you are lost in a desert at night and see a single distant fire. Is it a small campfire close by, or a raging bonfire much farther away? From your single vantage point with that single piece of information, it is impossible to know for sure. One reality perfectly mimics the other. Our cosmological observations taken in isolation suffer the same ambiguity. For decades we had a brilliant, exquisitely detailed photograph of one such fire. It was the oldest light in creation, the cosmic microwave background. This was our witness to the beginning, the afterglow of the Big Bang itself. It provided a snapshot of the universe at just 380,000 years of age, a picture of the infant cosmos in stunning detail. Within its subtle temperature fluctuations, we saw the seeds of all structure, the faint hum of those primordial sound waves, the very acoustic peaks that would later give birth to our baryon acoustic oscillations. The CMB gave us the initial conditions with breathtaking precision. It told us the universe was incredibly uniform yet contained tiny crucial imperfections. It was the foundation upon which our entire understanding was built. But it could not on its own deliver the final verdict. The problem was that the CMB could be telling several different stories at once. A universe with a certain amount of dark energy and a perfectly flat geometry could produce a CMB signal that looked nearly identical to a universe with slightly more dark energy, but which was gently curved like the surface of an immense, unimaginable sphere. The geometry of space and the density of energy were entangled, their effects degenerate, leaving us with a blurry range of possibilities. It was a powerful clue, a statement of profound importance, but it was not the whole truth. We needed a second witness, one that saw a different part of the story. That witness arrived with a bang, or rather with a series of bangs scattered across the recent history of the cosmos. Type Ia supernovae, the violent death throes of white dwarf stars. For a few brilliant weeks, a single one of these explosions can outshine its entire host galaxy, becoming a beacon visible across billions of light years. And crucially, because of the specific physics of their detonation, they all explode with almost the exact same intrinsic brightness. They are the universe's standard candles. If you know how bright a candle truly is, you can tell how far away it is just by seeing how dim it appears. In the late 1990s, teams of astronomers used these celestial lighthouses to chart the expansion of the universe through recent cosmic time. They expected to see the expansion slowing down, pulled back by the relentless gravitational grip of all the matter within it. What they found was the complete opposite. The expansion was speeding up. The universe was not just growing, it was accelerating, pushed apart by a mysterious repulsive force. They had discovered dark energy. It was a revelation that shook cosmology to its core, a Nobel Prize-winning discovery that revealed a universe far stranger than we had ever imagined. The supernovae provided our second great pillar of evidence. They saw the universe not at its birth, but in its adolescence and young adulthood. They measured the effect of dark energy at its present-day dominance. Yet even this monumental discovery had its own ambiguities. The supernovae were brilliant at measuring relative distances, telling us that a galaxy twice as dim was a certain factor farther away, but they struggled to provide an absolute, unassailable distance scale. and like the CMB, their measurements alone could not untangle the precise relationship between cosmic geometry and cosmic contents. They confirmed the existence of a ghost in the machine, this dark energy, but they could not fully reveal its nature or the shape of the stage on which it played. We had two powerful independent witnesses, one from the dawn of time, one from the recent past, and yet the case was not closed. The desert campfire remained an enigma. We were still staring at a cosmic illusion, a degeneracy that left the ultimate questions tantalizingly out of reach. What was the true shape of our universe? Was dark energy a constant, unchanging force, or was it something that evolved and shifted with time? To break the deadlock, we needed a third witness. We needed something that could bridge the vast gulf of time between the infant universe of the CMB and the modern era of the supernovae. We needed a cosmic Rosetta Stone, a single object of known size that could be seen in both the ancient past and the recent past, allowing us to directly measure the geometry of space between them. We needed a standard ruler, and that is precisely what the baryon acoustic oscillations gave us. This is the moment of convergence, the point where three great independent lines of inquiry born from different physics and measured with different telescopes meet to deliver a single, coherent and unyielding truth. This is where the sound of the Big Bang becomes the ultimate arbiter. The bell provides the missing link, the piece of evidence that locks everything else into place. Remember the size of that sound shell frozen in place when the universe became transparent. It was just under 500 million light-years across. We see the imprint of this ruler in the temperature patterns of the cosmic microwave background. There, in that baby picture of the universe, we have an exquisite measurement of how large that ruler was at the very beginning. It is our calibration point, our primordial yardstick. Then we look out into the universe of galaxies billions of years later. Using vast surveys that map the positions of millions of galaxies, we look for the echo of that same sound, that subtle preference for galaxies to be separated by that very same distance, 500 million light-years. And we find it. It is faint, buried in the cosmic web, but it is unmistakably there. Now we perform a celestial triangulation of cosmic proportions. We know the true physical size of the bow ruler from the physics of the early universe confirmed by the CMB. We can then measure its apparent size in the sky at different distances at different epochs in cosmic history. The laws of geometry are absolute. If you know the real size of an object and you measure its apparent size from a distance, you can calculate precisely how far away it is and determine the nature of the space between you. Suddenly, the degeneracy that plagued the CMB observations shatters. The CMB might suggest a curved universe with one recipe of ingredients is possible, but that same curved geometry would make the Bayer ruler at a distance of say 6 billion light-years appear a very specific predictable size. When we measure it, we check if it matches. If a flat universe with another recipe of ingredients is proposed, that geometry makes a different prediction for the ruler's apparent size. The Bayer acts as the ultimate tiebreaker. It forces the geometry of the universe to confess. By combining the exquisite data from the CMB with the unyielding geometric constraint of the BAO, the illusion vanishes. The possibilities collapse from a wide, blurry range into a single sharp point. And the answer that emerges is one of the most profound in all of science. To the absolute limit of our ability to measure it, our universe is geometrically flat. Imagine drawing an immense triangle with one corner on Earth and the other two corners on opposite sides of a distant galaxy cluster billions of light-years away. If you were to measure the angles of that triangle, they would add up to 180 degrees. Parallel lines on this cosmic scale remain parallel forever. They do not converge as they would on a sphere, nor do they diverge as on a saddle. This wasn't just a guess. It was a measurement, a verdict delivered by the echo of a sound wave from the beginning of time. The shape of the cosmos was revealed. But this was only half of the solution. Pinning down the geometry of space was a monumental achievement, but it simultaneously allowed us to attack the other great mystery, the nature of dark energy itself. The supernovae told us it was there pushing things apart. But what was Yuri? Was it the so-called cosmological constant, an intrinsic energy of space-time itself, proposed and then famously discarded by Einstein as his greatest blunder? A cosmological constant would be unchanging, relentless, its density remaining perfectly constant for all of time, even as space expands. Or was dark energy something more exotic, a dynamic field that could change over time, what theorists call quintessence? Perhaps its strength was different in the past or will be different in the future. The fate of the universe hangs on this question. To distinguish between these possibilities, we need to map the expansion history of the universe with extraordinary precision, especially during the period when dark energy began its hostile takeover, wresting control from the gravitational grip of matter. This is the period that neither the CMB nor the supernovae alone could map with perfect clarity. And this is where our standard ruler delivers its final crucial testimony. By measuring the apparent size of the bow at multiple points in cosmic history, 3 billion years ago, 6 billion years ago, 9 billion years ago, we can reconstruct a detailed frame-by-frame history of cosmic expansion. We can see exactly how the universe was behaving during that critical epoch of transition. It's like having a series of mile markers laid out across the cosmic highway. The supernovae are like a radar gun telling us the speed of cars near the finish line. The CMB is the photo from the starting pistol. The BAO provides the markers for every mile in between. When we combine all three data sets, the picture becomes whole. The supernovae provide the anchor in the recent universe. The CMB provides the anchor in the distant past. The BAO elegantly and robustly connects the two. Any cosmological model we propose must now fit all three datasets simultaneously. It must match the conditions of the early universe seen by the CMB. It must match the expansion rate seen by the supernovae today. And it must perfectly trace the historical path between them as laid out by the BAO. The constraints become overwhelmingly powerful. Cosmologists define the character of dark energy with a single number, a parameter they call the equation of state. It's a measure of the ratio of its pressure to its energy density. For normal matter, BW is 0. For a true unchanging cosmological constant, we must be exactly -1. For any other dynamic form of dark energy, Dw would be different from -1, or it might even change over time. As the data from the three great pillars of cosmology was combined, as the BAO measurements locked the expansion history into place, the value of W was calculated. The global community of scientists held its breath. The result was unambiguous. W is 1, not 1.1, not 0.9. To within a few percent, the value is precisely -1. Einstein's greatest blunder, it seems, was his greatest triumph. The simplest and perhaps the strangest explanation appears to be the correct one. Dark energy behaves exactly like an intrinsic unyielding energy of the vacuum of space itself. It does not appear to change. It does not weaken as space expands. In fact, because its density is constant, more and more of it comes into being, as the volume of the universe increases, driving the acceleration ever faster. With the geometry known and the nature of dark energy constrained, the final cosmic inventory could be taken. The great work of observational cosmology over the last century had led to this, a pie chart of the entire universe drawn with confidence. The numbers are now part of our standard model, the lambda cold dark matter model, a name that enshrines both the cosmological constant lambda and the mysterious cold dark matter required to form galaxies. The verdict is in. Our universe is composed of 68.3% dark energy, this relentless cosmological constant. It is 26.8% dark matter, the invisible scaffolding upon which all cosmic structure is built. And all of us, everything we have ever known, every star, planet, gas cloud, every species that has ever lived, every book ever written, every city ever built, all of it is part of a mere 4.9% of the cosmos. We are the baryon acoustic oscillations. We are the baryonic matter. We are a cosmic afterthought, a fractional percentage of reality living on a thin film of ordinary matter, surrounded by an ocean of the unknown. This is the universe that the sound of the Big Bang has revealed. A flat universe dominated by dark energy, whose ultimate character is a constant, unyielding push. And with this knowledge comes a chilling, awe-inspiring glimpse into the ultimate future. With U fixed at -1, the fate of the cosmos is no longer a mystery. There will be no big crunch, no collapsing back in on itself. There will be no big rip tearing atoms themselves apart. Instead, the future is one of majestic, perpetual and lonely expansion. The acceleration will continue relentlessly. Galaxies not gravitationally bound to our own local group are already being pushed away from us some faster than the speed of light. The light they emit today will never reach us. Their part of the universe is already receding over our cosmic horizon, lost to us forever. As we gaze into the far future, we see that horizon drawing ever closer. One by one, the distant galaxies will wink out of our sight, their light red-shifted into oblivion by the stretching of space. The night sky will grow darker, emptier. Eventually, our own Milky Way and its Andromeda-bound partner will merge, forming one last great Milky galaxy. But this island of stars will be adrift in an endless empty void. Beyond it, there will be nothing to see. Future astronomers, should any exist in that profoundly distant epoch, will look out into a sky of utter blackness beyond their own galaxy. They may never even have the evidence to deduce that there was a big bang, that the universe was once filled with other galaxies. The crucial clues, the CMB, the distant supernovae, the BAO, will have been stretched beyond detection. The universe will have erased its own history. Our time now, this very epoch, may be the only time in the long life of the cosmos when intelligent beings can look out and piece together the full story. This is the ultimate legacy of those primordial sound waves. They have not only told us where we came from and what the universe is made of, they have given us a profound, humbling, and perhaps fleeting glimpse of where it is all going. The Standard Model stands as a monumental intellectual achievement, but the story is not quite over. For in science, every great answer only opens the door to deeper, more subtle questions. And even this beautiful concordance model, confirmed by the cosmic echoes, is beginning to show the faintest of cracks. And so we arrive here at the edge of understanding. We stand before a map of the cosmos unlike any ever created, a three-dimensional ghost of space-time itself, drawn not with ink but with the light of ancient galaxies. Each point of light, each distant island universe is a marker in the dark, a beacon whose position was influenced billions of years ago by a whisper from the beginning of time. It is the culmination of a scientific journey so audacious, so utterly improbable, that it almost beggars belief. To think that we, a fleeting consciousness on a mote of dust, could decipher a sound we can never truly hear, a sound that propagated through a universe of plasma and light, when the entire cosmos was younger than a single human lifetime. This is the legacy of the baryon acoustic oscillations. It began not in an observatory, but in the quiet corridors of theory, as an elegant, almost poetic mathematical prediction. An idea that the titanic struggle between pressure and gravity in the primordial cosmic fluid would not simply vanish without a trace. Instead, it would leave behind a subtle, indelible preference, a characteristic scale imprinted upon the very fabric of reality, a ghost in the cosmic machine. For decades, this cosmic echo was little more than a beautiful abstraction, an elegant calculation trapped on paper, a prediction so bold it seemed to belong more to the realm of philosophy than astronomy. How could we possibly measure such an ephemeral fingerprint stretched by cosmic expansion across 500 million light-years of emptiness? The signal would be infinitesimally faint. Buried beneath the noise of countless other gravitational encounters, a single pure note lost in a cacophony of cosmic evolution. But the history of science is a history of pursuing the impossible. It is the story of building instruments to see the unseeable, of devising methods to measure the immeasurable. And so we began to listen. Not with our ears, but with our telescopes, which we transformed into the most sophisticated listening devices ever conceived. We learned to survey the heavens not just as a beautiful tapestry, but as a cosmic crime scene meticulously dusting for fingerprints, searching for the telltale clue left behind by the universe's violent birth. The first tentative detections were whispers in the data, tantalizing hints that the theorists had been right all along. Then, as our surveys grew deeper, and our methods more refined, the whisper became a voice, and the voice grew into a chorus. The faint statistical preference for galaxies to be separated by a specific distance was no longer a statistical fluke. It was a resounding, undeniable signal, a standard ruler stamped onto the large-scale structure of the universe. We had found it. We had measured the echo of the Big Bang. This discovery represents more than just a triumph of observation. It is a grand synthesis, a beautiful and powerful convergence of seemingly disparate threads of cosmological inquiry. Think back to the cosmic microwave background, that baby picture of the universe we explored in the heart of our journey. We saw the sound waves there frozen in time at the moment of recombination, visible as subtle hot and cold spots in the afterglow of creation. Those spots told us the precise size of the sound horizon, at that instant when light was finally set free. The baryon acoustic oscillations are the grown-up version of that same phenomenon. They are the living legacy of those primordial ripples, no longer visible as patterns of temperature in a sea of light, but as patterns of matter in a universe of galaxies. The Bayo measurement is the ultimate bridge connecting the two epochs. It confirms with breathtaking precision that the very same physics that governed the plasma soup 380,000 years after the Big Bang also sculpted the distribution of billions of galaxies over 13 billion years. The size of that primordial ripple measured in the CMB perfectly predicts the size of the galactic bubble we measure today once you account for the universe's relentless expansion. It is a stunning cross-verification, a cosmic Rosetta Stone that allows us to read the history of the universe in two different languages, the language of light and the language of matter, and find that they tell the exact same consistent and extraordinary story. This ruler, this celestial yardstick, is not just an artifact of the past. It is our single most powerful tool for interrogating the present and charting the future of the cosmos. Because we know its original physical size with incredible accuracy from our CMB measurements, we can use it to measure cosmic distance in a way that is profoundly fundamentally geometric. By looking at distant galaxies, we are looking back in time. We can see the ghostly BAO sphere as it appeared billions of years ago. The apparent size of that sphere in our sky tells us with a precision that rivals any other method just how far away it is. By doing this for galaxies at different epochs, we assemble a meticulous history, a precise record of how the universe's rate of expansion has changed over time. And it is in the fine details of that history that we confront the most profound and unsettling mystery in all of science dark energy. Our BAO measurements have confirmed beyond any reasonable doubt that the expansion of the universe is not slowing down as gravity would demand. It is accelerating, pushed apart by a mysterious pervasive energy that seems to be woven into the vacuum of space itself. The baryon acoustic oscillations have given us the sharpest portrait yet of this cosmic antagonist. They have allowed us to track its influence back through cosmic time, revealing that for the first several billion years of the universe's life, gravity was winning. The expansion was as expected decelerating. But then as the universe grew and matter diluted, a tipping point was reached. The persistent, unyielding pressure of dark energy began to dominate, and the cosmic acceleration we witness today began in earnest. The sound of the Big Bang has become our primary tool for characterizing this phantom force that dictates our universe's ultimate fate. It has become a testament to human ingenuity, a story of how the faintest whisper from the dawn of time can be used to illuminate the deepest darkness in the cosmos. But this story, our story, is far from over. The journey of discovery does not end here. It is only just beginning. For we are now entering a new golden age of cosmological surveying, an era where the foundational work of the past gives way to a new level of precision, a level that might finally force dark energy to give up its most fundamental secrets. High in the Arizona desert on Kitt Peak, a new instrument has opened its eye to the cosmos, an instrument built for this single purpose. The Dark Energy Spectroscopic Instrument, or DESI, is a marvel. It is not one telescope, but 5,000 working in perfect unison. 5,000 robotic fiber-optic positioners, each acting as a tiny independent eye, can pivot and fix upon a distant galaxy in mere seconds. In a single exposure, DESI can capture the spectra, the chemical fingerprints and precise distances of 5,000 galaxies at once. Its mission is a census of the universe on an unimaginable scale. Over its 5-year primary mission, it will measure the positions of more than 40 million galaxies and quasars, creating a map of our cosmic neighborhood, with a volume and a fidelity that dwarfs all previous efforts combined. Imagine constructing a map of a vast ancient forest. Previous surveys were like taking aerial photographs capturing the general layout of the woods and the largest clearings. DESI is like sending out an army of surveyors to measure the exact location, height and age of every single tree in that forest. With this unprecedented statistical power, DESY will not just measure the bioscale, it will dissect it. It will map the subtle variations in the biosignal across the sky and through different cosmic epochs with exquisite detail. This will allow us to ask deeper, more challenging questions. Is dark energy a true cosmological constant, an unchanging energy of space as Einstein first speculated? Or is it something more dynamic, something that has changed in strength over the eons, a phenomenon we call quintessence? DESY's precision will be so great that it will be able to test the very foundations of our understanding of gravity. It will measure not only how galaxies cluster, but also how they move, probing the intricate dance between the expansion of space and the pull of gravity on the largest possible scales. If there are any subtle deviations from Einstein's theory of general relativity, any cracks in that century-old paradigm, it is on these vast scales that they are most likely to appear. DESY is looking for them, and it is not looking alone. Drifting silently in the cold vacuum of space far beyond the Moon is a new sentinel launched by the European Space Agency Euclid. Freed from the blurring effects of Earth's atmosphere, Euclid will conduct a survey of a third of the entire sky, creating a 3D map of breathtaking scope. But Euclid has a dual-pronged approach to solving the dark energy mystery. It will measure the BAO feature charting the geometry of spacetime, but it will simultaneously measure the subtle warping of light from distant galaxies caused by the gravity of intervening dark matter, a technique known as weak gravitational lensing. This allows Euclid to map not only the expansion history of the universe, but also the growth of its structure, the clumping of matter, into the cosmic web we see today. By combining these two independent, powerful techniques, Euclid will subject our cosmological model to the most stringent tests yet. If the history of expansion measured by the BAO ruler does not perfectly align with the history of structure growth measured by gravitational lensing, it could signal the existence of new physics, a signpost pointing us toward a deeper, more complete theory of the cosmos. Looking even further ahead, NASA's Nancy Grace Roman Space Telescope is poised to revolutionize the field once more. With a field of view 100 times larger than that of the Hubble Space Telescope, Roman will be able to survey the universe with an efficiency that astronomers of a previous generation could only dream of. In a matter of months, it will gather more data than Hubble has in over 3 decades of operation. It will peer deeper into the infrared, capturing the light of galaxies so distant that their light has been travelling towards us for over 10 billion years. Its vast survey will provide a BAO measurement from an era when the universe was young and dark energy was only just beginning to make its presence felt. This will give us a critical lever arm in time, allowing us to chart the entire saga of cosmic expansion, from the deceleration dominated by matter to the acceleration we experience today, all in a single coherent dataset. The sheer volume of information from these upcoming surveys, DESY, Euclid, Roman, is almost beyond comprehension. We're entering an era of cosmic big data, where our ability to analyze and understand the information we gather will be just as challenging as building the instruments themselves. It will require new computational techniques, artificial intelligence, and the coordinated effort of thousands of scientists worldwide. But this is what we do. It is who we are. We are the universe made conscious, and our deepest impulse is to understand the magnificent, sprawling, and often baffling home we inhabit. The story of the baryon acoustic oscillations is ultimately a human story. It's a story about listening for the oldest sound in creation, a sound that no longer travels as a wave but exists as a memory, an architectural blueprint for the cosmos. That primordial sound wave born in the fire of the Big Bang did more than just leave a faint echo in the distribution of galaxies. It was part of the process that shaped everything. The very structure of the cosmic web, the vast filaments and voids, the great walls of galaxies and the empty deserts in between, all bear the subtle imprint of those first acoustic reverberations. They provided the initial density variations, the seeds of structure, around which the gravitational scaffolding of dark matter would later form. And it was within that scaffolding that ordinary matter, our matter, would eventually gather to form the stars and galaxies we see today. So when you look up into the night sky, you are not just seeing a random scattering of lights against a dark backdrop. You're seeing a pattern, a deep and resonant order, whose fundamental frequency was set by a sound 14 billion years ago. The universe has a memory, and we have finally learned how to read it. We have learned to see the invisible and to hear the inaudible. This quest has taken us from the chalkboards of theoretical physics to the pristine, clean rooms where robotic eyes are assembled from the lonely mountaintops of our planet to the silent sunlit orbits of deep space. It is a journey that reveals not only the nature of the cosmos, but also the remarkable, persistent and unyielding power of human curiosity. We are still faced with profound questions. The nature of dark energy remains a gaping hole in our understanding, a challenge to the very foundations of physics. But we are no longer lost in the dark. We have a map, we have a ruler, we have a direction, and we have the echo of a primordial sound to guide us, a constant reminder that even in the vastest, darkest voids of space, we are connected to the very beginning of everything. The silent sky is not silent at all. It is ringing with the faint cosmic hum of its own creation, and we finally are here to listen.